Now we will understand the concept of atmospheric pressure. So, what is the atmospheric pressure? Let us say this is our Earth. Okay, it is not exactly a spherical object, it is more like an ellipse. So, approximate figure you can understand like this. Okay, so above the Earth, we have a layer of atmosphere or an envelope of atmosphere. Okay, you must have studied about the various layers: tropospheric layer, stratospheric layer, ionospheric layer, mesospheric layer, exosphere, etc. So let us say all these layers we can represent by an outer ellip ellipsoid structure, right? Now you understand by now that whenever there is an object or a medium like air, which is similar to any liquid, there will be a pressure at every depth. The outer atmospheric layer is exerting pressure on the inner atmosphere, and it progressively increases as we move towards the earth because the layer of atmosphere is increasing, or we can understand as the depth, is increasing, right? We understood the pressure increases with depth for a liquid, so similar case. So at the surface of the earth, what is the pressure due to the entire envelope of the atmosphere above it? That is what we are interested in, and that is what we define as atmospheric pressure. So what is atmospheric pressure? Atmospheric pressure is nothing but the pressure exerted by the air envelope surrounding the earth. And at the surface of the earth, what is the pressure due to this atmosphere? That we need to understand and find out. So let us do that. So scientists used to perform experiments uh, to understand the atmospheric pressure and its magnitude, right? So there was a scientist by the name of Guercke. If you see here, we may not be able to pronounce his name correctly. Apologies for that. But this German scientist, he performed an experiment. What was the purpose? He wanted to understand the force exerted by the atmospheric pressure on objects. So what he took two hemispheres made of copper. Okay, two hemispheres made of copper. The diameter of each of the hemispheres he took was 10 inches, sorry, 20 inches, and these were hollow hemispheres. So it was made of copper, but this hemisphere was hollow inside. Similarly, this hemisphere. Now he tried to join them. Okay, so he joined them like this. And because they are hollow, inside there will be air, outside definitely you have air. So when he joined them and tried to separate them initially, it was easier for him. Okay. However, in the second case, what he did was when he joined the two hemispheres, airtight seal so that no air can go inside, only the air inside is there. And he made an arrangement, a small outlet to pump this air inside the enclosure out so that there is vacuum or near vacuum inside it. Now, when he tried to separate these two hemispheres, it was very difficult for him. And ultimately, he succeeded only when he used the help of 8 horses. 4 horses on the right side, 4 horses on the left side, trying to pull. So, that much energy was required to separate the hemispheres once the air inside the hollow enclosure was removed. That tells you that the force exerted by the atmosphere or the air outside, initially it was balanced by the force exerted by the air inside. That's why it was easier to separate them. Less force was required to pull it apart, right? But when you removed the air inside, there is only the force or pressure exerted by the air outside, which is trying to bind these two hemispheres. And therefore, if we apply that external force now, we don't have the support of the air inside to help us separate these hemispheres. That tells us that in the second case, the force required to separate the hemispheres is exactly equal to what is the force exerted by the outside air on this hollow hemispheric enclosure to keep it joined. So that is how this scientist uh, estimated that the atmospheric pressure is a very significant quantity to be understood. Now, there was another scientist by the name of Torricelli, which we this name we mentioned a short while back as one of the units of atmospheric pressure, right? So this scientist, Italian scientist, he tried to find a formula and a measurable value for the atmospheric pressure. For this, what he took was he took a 1 meter long tube, a very thin tube of length 1 meter, and he filled it to the brim with mercury, to the brim with mercury. Okay, and he closed the open end with his thumb tightly so that the mercury will not flow out. Okay, let us say he closed it with his thumb. So I'm not able to surely draw this thumb. My drawing skills are not that good, but let's understand there is a seal here. Sorry, there is a seal here. Okay, now once he sealed it tightly with his thumb, he inverted this tube and placed it inside a large trough which was filled with mercury. Okay, this is the trough which is filled with mercury, and he inverted this tube, and he did not remove his finger while inverting, so there is no chance that the mercury inside the narrow tube would able to be uh, you know flow into the trough initially. So here the seal was there, and he once he um, this was the seal, let us say, and this mercury was already there inside that tube. So initially it was totally filled because he sealed it. Now inside, once he dipped it inside the trough, he removed this seal. He removed this seal. So allowing the mercury inside to flow out into the larger trough. Okay. Now what happened was an interesting phenomenon happened. The mercury started flowing out of the thin tube and into the larger trough. Sorry, I'm just erasing small lines to make you feel how the mercury is, you know, flowing out. So a part of the mercury flowed out, and after that there was an equilibrium. And he measured this height of the mercury, which is still there in the thin tube. So above the surface a level of mercury in the trough, the mercury in the thin tube was having a height of 76 centimeters when this experiment was performed at sea level. Okay. Now, the entire mercury could have flowed out, but it did not. That means there was something which was trying to push this mercury to remain here. Correct? Agreed? And if you see, if I filled up this test tube initially with mercury up to the brim and I've sealed it, so when you are inverting it and some mercury is going inside the larger trough, this part is technically a vacuum. It was called Torricellian vacuum. It might have a very, very um, uh, small content which was nothing but filled with mercuric vapors. Beyond that, nothing. So we can technically, so this vacuum spelling I did not write. So this was technically a vacuum, right? Okay, this was technically a vacuum. Okay, so that means there is no force which is trying to push the mercury down other than the weight of this mercury column. Okay, the weight of this mercury column is trying to push it down. There is no other force of any air column above it, right? The only force on the on this mercury in the thin tube is the force downwards, which is the weight of the mercury. The force upward is due to the pressure exerted by the mercury inside here, and technically you can understand it like this, that this trough has an open surface, so the atmosphere is exerting pressure on this surface, correct? Air column above this trough. Now, if I take a point on the surface in the trough, let us say this point A, and another point inside the thin tube, but at the same horizontal level, let us say this point B. Okay. Now, at point B, we will understand what's happening. So, at point B, downward force is what? Downward force is nothing but weight of the mercury column. So, weight of the mercury column above it, right? Which is to a height of 76 centimeters from the surface level. Okay. So what is this weight? Weight is nothing but mass of mercury of this much height multiplied by acceleration due to gravity. Okay, weight is nothing but a force. So force is equal to mg, we understood. Now what is the mass of this column? Mass is nothing but volume into cross-sectional area. So just understand this as a small cylinder. Okay, so it has a volume. Okay, and this volume multiplied by density is nothing but mass. So mass upon volume is density. So mass is equal to volume into density. This is density of mercury and multiplied by G. And again, volume is equal to area of the cross section. This is the cross section. Area of the cross section multiplied by height H. Let us say this 76 centimeter is the height. So area into H will give us volume multiplied by density multiplied by G. This is the downward force acting at point B. Okay. And what is the upward force? Because now it is in equilibrium. Okay. What is the upward force? Upward force at B is equal to atmospheric pressure. Why? Because a short while ago we understood that the pressure at any depth inside a liquid is equal to uh, H rho G, right? And for the point A which is on the surface, point B which is on a horizontal level, the pressure should be same. And at point A, the pressure is due to atmosphere now. This is another fluid, let us say. So at atmosphere. So technically this force is the force which is trying to push mercury inside. Okay. So that means the pressure at point B, which is trying to push the mercury up, is due to the atmospheric pressure. Imagine that the atmosphere is pushing this mercury down, so that part of the mercury is going up. Okay, so pressure at atmosphere is the upward force. Now, when equilibrium is there, they both are balanced. So we can write pressure atmosphere is equal to down weight of the mercury column, right? Weight of the mercury column. I just move my picture image to this side for clarity. Mercury column at B, which is nothing but pressure atmosphere equal to A into H into rho into G. Now, if you see area of cross section multiplied by H multiplied by rho multiplied by G. Now we have equated pressure with this. We should not equate. This is force due to the atmosphere. That is why uh, the dimensions are not balancing. So it is force due to the atmosphere. From this force, we will calculate pressure, which is force per unit area. So force due to atmosphere. Now what is the force due to atmosphere? Pressure of atmosphere multiplied by area of cross section, because this force is acting here also, right? So pressure is nothing but acting at this point. So pressure into this cross section is this force, right? Which is equal to this force. I mean, this force is at this point I'm calculating this force. Okay, so pressure at atmosphere into A is equal to A H rho G, and A will get cancelled out. So we get pressure at atmosphere is equal to H rho G. And when you calculate this uh, using the values for mercury, we get pressure atmosphere equal to height of the mercury column we said is 76 centimeters, which is nothing but 0.76 meters. Rho density of mercury is 13,600 kg per meter cube, and H rho G is 9.8 meters per second square. So if we calculate this, this comes out to, as mentioned in the left side, it is 1.05 into 10 raised to 1.01 into 10 raised to 5 Newton per meter square or Pascal. So this is equal to 1 atmosphere. Okay, so it can be used as a conversion unit. Whenever you want to convert pressure from SI units of Newton per meter square or Pascal into atmospheric units, then we need to use this multiplying factor. Okay, let us say if somebody says at a certain point the pressure is 2 atmospheres, that means it is equal to 2 into 1.01 into 10 raised to 5 pascals. Or otherwise, if someone says pressure at a point is, let us say, 100 pascals, just an example, then in atmospheres, if you want to convert it, you need to divide it by this multiplying factor, these many atmospheres. So got it? So this is the concept of atmospheric pressure and how the atmospheric pressure unit 1 atmosphere can be converted into the SI units and vice back. Okay, so in the next video, we will delve into the concept of buoyancy, which is another important property of the fluids.